Okay, now I want to tell you about a concept that is often useful, and surprisingly, one of the places that you run across this concept most frequently and most usefully is in the biological sciences. And this is actually related to a dipole, which is one of the reasons that I spent so many examples with the dipole. And so you're very familiar with what this looks like. And I want to ask the question, well, let me tell you the question I'm not going to ask. I'm not going to ask about the electric field of this object. Rather, I'm going to imagine, what if this object were immersed in an external electric field? And for the sake of simplicity, I will make this external field uniform. And the question I'd like to deal with is, what happens to the dipole when it is in this external field? That subscript ext there is to make it clear that the field that I've just drawn here is, of course, not due from the dipole, but from something else. Well, your first thought might be, well, there's a couple of charges and they're going to wander off based on whatever force they have to experience from this field. But it's not quite that simple, because remember, these two charges being opposite signs are attracting each other. So they're attracted to each other, so there's a force binding them together in addition to whatever force the external electric field applies on each of the two charges. And the force binding them together is typically pretty strong. And so we will assume, and I will give you an example in a little while that will make this a very strong assumption. We'll assume that the two charges that make up the dipole stay together. They specifically, they maintain a fixed distance from each other, a distance that I will label d. Okay? So now the question is, what does happen to it? Well, let's think about it physically first. Each one is going to experience a force, and we can think about that force. The positive charge is going to experience a force that will point like this. Right? The negative charge will experience a force that points in exactly the opposite direction. So its force will be like that. Okay. And maybe you've seen this before, because what happens is this force is going to act this way, this force is going to act this way, and if we assume that the two charges stay together, okay, then what will end up happening, and I'm not going to reiterate everything that you learned in 114, I will simply say that the result is that you have a force off at some distance here, force at some distance here. In other words, we have these two forces are acting at two distances away from what? An axis of rotation. This dipole is actually going to rotate in this field. Okay, the force, or the pair of forces that the external field applies to the two charges creates two torques. Okay. The imaginary line joining these two charges is that, and the axis of rotation, assuming that these two things have the same mass, the axis of rotation is going to be there. Okay, and so the distance that each one is from the axis of rotation is going to be, in this case, d over 2. If the masses are different, those distances will be different, but that's all right. Right now, we won't worry about that. And so the result is we get a couple of torques. All right. So let's think about that. Specifically, let's calculate those torques. Okay. Pause the recording just for a moment. Okay, sorry for that interruption. Something happened. Okay, so I was just calculating the torques that happen on each of the two charges. And again, with the assumption that the two charged objects carry the same mass, then the center of mass will be halfway between them, and that will be where the axis of rotation is located. If the two masses are different, then the center of mass will be shifted closer to the more massive particle, and the amount of shift will be proportional to their masses. We'll see that in an example. But in any case, for the moment, we assume they're the same masses. So the moment arm, or the lever arm, depending on what terminology you like, is going to be d over 2 for each of them. So for the positive, well, the total torque is the torque on the positive charge plus the torque on the negative charge. And remember, a torque is a vector, right? The torque on the positive charge is going to be its moment arm, which is d over 2, crossed with the electric force on it. So the moment arm, 1/2 d, and we'll treat that as a vector, crossed with the electric force on it. The torque on the negative charge is going to be the same, and I'm not going to bother telling you. I will let you work it out for yourself that the directions of these two torques end up being the same. You should be able to figure that out if you remember the right-hand rule, which maybe you don't. If not, we can talk about it in class. But in any case, whether you know it instantly or figure it out or whatever, these two torque vectors end up pointing in the same direction. And therefore, the total torque, being the sum of them, is just 1/2 d, 1/2 d, 1/2 d plus 1/2 d gives us just d cross f. Okay, so far so good. I suppose before I move on, maybe I should draw these torques in. Let's see. These orange arrows, these are the forces. The moment arm, do that in red, I guess, is going to be this. That's 1/2 d. The moment arm, remember, points from the axis of rotation to the point where the force acts. So on this one, the force is acting, I guess I'm going through it with you. Oh, well, that's fine. The moment arm is this way, the force points this way, and so we cross the moment arm vector into the force vector, and you remember how to do that. You apply the right-hand rule, whichever way you like. This is how I do it, with the palm of my right hand. So you put the two vectors tail to tail, and then with the palm of my right hand, I'm going to push the first vector, 1/2 d, into the second vector, that's the force, like this, and so my torque vector is pointing into the board, and that's the negative, that's the torque on the negative charge. Meanwhile, over here we have the force acting this way. The moment arm for the positive charge is here, from the axis of rotation to the point where the force acts. And so again, you cross the moment arm into the force, and so putting them tail to tail and then apply the right hand rule, once again you see the torque is pointing into the board as I promised. All right, so that's positive torque. So they add together. Great. The force each one experiences is of course, an electric force. Whatever the charge is, it could be, if there are two protons, then the Q would just be the elementary charge that we represent with the symbol E, or these could be whatever atoms. They could be, it could be a hydrogen atom and an oxygen atom. That would give you a hydroxide. Whatever they happen to be. Anyway, the charges, and so the torques, or the total torque really, is D then cross Q times E. Okay. Q is a scalar, so I'm going to, for no obvious reason, pull that out and put it in front. And the reason I did that actually is so that I can define a new thing. This product of the charge on each of the objects multiplied by the distance between the two objects of the dipole. In other words, this expression assumes that our dipole is constructed from two objects that have equal and opposite charges separated by a distance d. Okay, this construct is defined, is given the symbol p. It's a vector, as you see, the charge times the vector distance. And is defined as Q times d. This is known as the electric dipole moment. You might recall from 114 that, or from your first quarter of physics, whatever number your school called it, you might remember that anytime you see the word moment, that is an old word implying rotation or turning, and it does here too. So the torque then can be written in a nice simple way. Sorry, I keep running over my cables here. The total torque that our dipole experiences is simply P cross E. Okay. We can simplify this down a bit, by the way. You'll remember that when you take the cross product of two vector quantities, you obtain yet another vector, and so we do here. And the magnitude of that vector is gotten by the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. Okay, and so for most practical purposes, this is the expression that you end up actually wanting to use. Okay, and so we can calculate that. For example, if I had, let's just make up some numbers here. And I'm literally making up the numbers right now. Let's suppose we had two objects, each of which had a charge of, well, let's keep it simple. Let's say it's a proton and an electron. Why not? So it'll be, the charge will just be E, 1.602 times 10 to the minus 19th coulombs. And let's suppose they are a distance, let's see, the proton and electron, really what we're talking about is hydrogen atom in its resting state, its so-called ground state. The radius of the hydrogen atom is 5.29 times 10 to the minus 11 meters. Okay, and if I immerse that in an external electric field, so I have a hydrogen atom and I'm just floating in space, and I suddenly flip on some external electric field, let's say 4 times 10 to the negative 6 newtons per coulomb, right? And choose a random angle, let's say 30 degrees, which is pi over 6. Is that what I did over there? I don't know. Anyway, then the torque that the thing experiences is going to be P times E times sine of theta, but the electric dipole moment, P, is Q times D, E sine theta. And so then we substitute in the numbers, and we come up with that the magnitude of the torque is 1.602 times 10 to the minus 19th coulombs times the distance between them, 5.29 times 10 to the minus 11 meters, times the electric field, which I said was 4 times 10 to the minus 6 meters, and then sine of pi over 6 radians, which is 30 degrees. And you plug in those numbers, and I have no idea what that answer is. So I'm going to pause the recording and calculate it. Okay. And I calculated it, and I got 1.7 times 10 to the negative 35 Newton meters. And just a quick sanity check on the units here. Coulombs times, oops, this should be newtons per meter, that's my mistake. Presumably you were yelling at the screen. No, it's newtons per coulomb here. Now the units work out. And this, by the way, I'm not erasing this, and I'm not going to re-record this, because this is an important thing. This is a sanity check. This is how you know whether you went wrong. The reason I was staring at this, the reason I paused the recording and fixed it, because my units weren't working out. But I checked, and I finally figured out where my problem was. So I know that since I'm calculating a torque, I know the answer has got to come out with units of newtons times meters. Okay? So I couldn't have, my coulombs had to cancel out, and they weren't canceling out. So coulombs in the numerator, coulombs in the denominator, those canceled out. Newtons times meters, that's it. Yeah, okay, so we're good. All right, so that's that. What I'm going to do in the next recording is a considerably more complicated example, but one that is useful, as I say, in the biological sciences. So let's do that next.